Watch this pristine concrete slab. A jagged fracture rips across the surface. No impact, no heavy load pressing down. It just breaks. This happens constantly. Concrete structures all over the world routinely tear themselves apart from the inside out, often before they are even put into service. This schematic is a bridge deck crack map. The dense vertical lines track full-depth fractures that appeared spontaneously across the span. Engineers map these failures to track the progression of internal collapse. These openings allow water and corrosive road salts to penetrate the core. That moisture reaches the internal steel, initiating a cycle of rust and degradation that can cut a bridge's service life in half. These failures aren't caused by traffic or weather, but by a series of predictable chemical reactions occurring deep inside the material's own structure. Concrete is a dynamic mixture of cement, sand, stone, and water that continues to change long after the initial pour. To make the heavy mixture liquid enough to flow into a mold, workers must add extra moisture, known as water of convenience. Once the concrete is in place, that extra water eventually dries up and evaporates, leaving behind billions of microscopic empty voids. As it loses that water mass, the concrete tries to shrink inward to fill up those new voids, but it is poured over a rigid skeleton of steel rebar that refuses to budge. The concrete attempts to contract while the steel holds it firmly in place. This creates a state of internal tension that builds until the material literally pulls itself apart. To understand how that tension becomes strong enough to snap a bridge, we have to look at the material on a nanometer scale. Down here, you see the calcium silicate hydrate, or CSH, gel. This is the primary chemical binder that glues the structure together. While a bridge pier looks solid to us, the binder is actually a porous network full of microscopic canyons. The total surface area hidden inside those pores is staggering. If a single sugar cube-sized chunk of concrete were unfolded, its internal walls would cover 2 full-size tennis courts. Every millimeter of that massive internal surface is a potential site for the material to begin failing. When water evaporates from these tiny pores, the liquid shrinks. Its surface curves inward, forming a tight meniscus. This creates capillary stress. The shrinking water develops enough surface tension to grip the solid walls, pulling them towards the center. Across the entire structure, the dry outer layer is pulling inward with this force, while the wet inner core stays stationary. The internal pressure continues to climb until the tension exceeds the structural limits of the gel, and the binder snaps. A large-scale crack in a bridge is simply the cumulative effect of trillions of these microscopic pores losing their grip. This isn't an unsolvable problem. Engineers have spent decades developing methods to neutralize these forces during the curing process. Since we cannot stop evaporation entirely, the solution lies in altering how the water interacts with the material's pores. One approach uses shrinkage-reducing admixtures, or SRAs, which are added to the wet mix before it is poured. An SRA weakens the surface tension of the pore water. As the water evaporates, it no longer has the physical strength required to pull on the pore walls. Another method is internal curing, which uses pre-wetted porous stones called lightweight aggregates. These stones act as internal reservoirs. They are saturated with water and distributed throughout the concrete mix. As the concrete begins to dry and tension builds, these stones release their water into the surrounding pores, relaxing the internal stress before a crack can ever start. By identifying the specific physical triggers for shrinkage, engineers can now build structures that remain stable for decades. The next time you cross a concrete bridge, you're standing on a structure where these internal forces were managed at a microscopic level.